Sorry, the break took a little bit longer. I mean, yeah, we were discussing about like 你知道今年我们系上要被评鉴，所以要比较麻烦。你问一下你们觉得说，你们这一届是现在是2个学期的专题嘛？你们知道吗？还是你们根本不知道？你们现在不是理论上你们是大3吗？你们不是正在做专题中？大2。哦，你们是大2，大2。好，没关系。但你知道说你们的专题应该是两学期的嘛？对不对？两学期的。所以说2学期的专题应该就是以前其实中央职工以前是3学期的专题。那我们以前评鉴的时候，那个效果还不错，就是人家讲说我们做3学期的专题有特色什么东西。那后来因为前任的主任就是应该说，很早以前我当副主任的时候，就是那个张家慧老师当主任的时候，那时候把专题从2学期变成3学期。那时候讲说第3学期可以是继续做专题，或者说是交换学生，或者说是实习都可以这样子。那推了很多年嘛，但是上任主任就是苏博奇老师当主任的时候，把这个3学期又改回2学期了。那我们上次的那个评鉴的时候，人家说啊，那个资工系我们这边做3个学期专题很有特色啊，什么什么什么。那但是我们今年要被做那个评鉴的时候，就变2学期了。所以现在就在想办法去圆啊，对啊，要怎么样子去讲这个东西？你们觉得3学期的专题比较好，还是2学期专题比较好？你们自己觉得？还是你们根本就觉得没差，没做过不知道？就是其实那个是一个必修啦，对，等于说。我觉得苏若琪老师那时候当主任的时候，大概是想要减掉一些必修课嘛。那他也是想说，如果说你要做交换学生，或者说做专题，做那个实习，你们就可以自己去申请，也可以，这也是没错啦。其实不一定要从实习这个方向去走，对。但是讲到这个实习，顺便问一下。你们有多少人对实习有兴趣的？实习，还是也是不知道？你们现在都还太年轻。对，其实我会建议你们在大学的时候至少去实习1次。我觉得第一点不是为了赚钱啊，当然实习有钱赚也不错啦。对，因为资工的去实习通常配也还不错，但重点是在说实习，你可以看一下外面业界在做什么东西，跟学界的其实很不一样，就是可以了解一下业界的这种生态，我觉得是很好的一个经验。那这是第一点。那第2点是说，你们将来如果说要推甄，或者说要出国申请学校的话。实习的经验都很有帮助，对，所以我会觉得说，你们如果说有兴趣或者说有时间的话，你们应该要去试试看，申请看看，其实不会那么难。那我会觉得说是一个很好的经验，对 ，anyway， 好，那其实我们系上有很多公司都跑来。就是讲白一点就要人呐，对，那就是有很多我们你们顺便问你们有多少人有 subscribe 那个脸书的那个系上的那个网页，那个系上的那个网页，还是你们根本现在也不用脸书了？你们现在用脸书，你们现在的人用脸书，大概会觉得是老一代人在用的，是不是？啊，你们现在都用什么？都用 Instagram， 都有。对啊，这个说不定我们系上也要 migrate 到你们常用的这种平台去。我的意思是说， 像学校，譬如说像我们系上有公司跟我们征才，就是有这种 information 的时候，我都是请那个系上同仁帮忙把这个 information，就是发在那个系上的这个就是脸书的这个粉丝团呐，就是社团呐。所以说你们如果说对实习啊，像我刚刚讲的这些东西有点兴趣的话啊，想要看一下有哪一些实习机会，除了学校的这种就是这种公司来这边这个征才的这种 occasion 以外，你们其实3不5时在脸书的那个资工系的那种社团上都有发，那你们应该要去看一下，对，好不好？这也是先跟大家讲一下哦，这个应该对大家这个将来也都有一些帮助的。好，那回来到那个 OK， 我们刚前面讲的 OK。Yeah, because you have like a large range of keys, right? And the size of your table is limited, okay? So obviously, I mean, the collisions happen, I mean, from time to time, okay? So you do need a way to resolve the collision, okay? So the first way to resolve the collision is what we call open addressing. Okay, so actually previously we talked about one way. It's you know, if there's a collision, we try to use a linked list, right? We try to use linked list to resolve the collision. That can also be considered as like a collision resolution. Okay, so. But if you do not want to utilize like additional storage space, okay, because linked lists obviously require additional storage space. But if you do not want to, you know, waste your storage space, you want to use like a, you know, hash table to deal with like a collision, then okay, the first way is open addressing. Okay, so the insertion, okay, is going to prop the table until empty slot is found. Okay, so there's a probbing process there. So the high level concept is going to be like this. The hash function, okay, depends on the key and the prop number. So it becomes like you know, your key, which is like from this universe, and this 0 to n-1. Okay, there's a non-number indicating the prop number. Okay, so for example, giving a key k, and the probbing number can be like from 0 to 1 to 2, blah 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 to n-1. So obviously each of these you know, function will map to one place in the hash table. But remember, we only have m space in the table. So supposedly these numbers should be a permutation of 0 to n-1. Okay. 因为我们现在就譬如说，你现在同样的 k 哦，同样的这个 key 哦，那你可以 prop 0次 ，prop 1次 ，prop 一直到 prop n-1次嘛。那这每一次应该要被映射到不一样的地方嘛，对不对？因为你这个理论上是在想办法去 map 到这个 table 上的某一个位置。那这个位置理论上，这个应该要想办法去搜寻 table 上所有的可能的位置才对。所以这些其实理论上它就是一个0到 n-1的这些数字的一个 permutation， 就是这个顺序的改变而已。OK， 那 table 当然有可能满哦 ，fill up，and the deletion is difficult。OK， 就是在你考虑到 problem 的时候，就是说如果说你要考虑到这个 collision resolution， 就同时要考虑 collision resolution， 然后那你在这种情况下要考虑 deletion， 这是会比较困难的因为但是不是不可能不是不可能。基本上hash table 应该说we need to insert often and search often, but deletion doesn't happen very often. Okay, deletion happen very rarely. Okay, this is like an assumption for hash table. Okay. 那这个是一个例子This is an example. Okay. For example, if you want to insert key equal to 496. So first time, okay, you prop like a H4960. So this may be mapped to this index, but obviously this location has been taken. Okay, so there's a collision. So next you try to prop H4961, and then this will be mapped to here. Okay, again this space has been taken, so obviously we have a collision again. The third time, okay, you try H4962, and then because this is like a space has not been used, so you can safely insert this key here. Okay, so it's like you keep checking if a space is available. If not, you keep propping until a space is found. I mean, in this example, okay, we don't even provide this hash function. This is a concept, okay, concept. You just keep doing that until a space is found, okay. And this mapping, okay, suppose, okay, if you keep having the collision, 如果你一直有 collision, 那 you are going to explore the whole table supposedly, okay, until the probing number reach like n-1. If you still cannot find anything, then supposedly the table is full. Okay, the table is full. Okay, so search this is for the insertion. How about the search? Search basically uses the same prop sequence. Okay, so it's going to try to find, for example, like 496. The first time, 496 it will map to here. It's not 496. Okay, so second time it try. This one it's 586. It's not 496. So again, it's not this one. The third one is it found like it's here. So it's going to use the same sequence. It's going to terminate successfully if it finds the key, and unsuccessfully if it encounters an empty slot. Another possibility is, okay, it doesn't encounter empty slot, but the probing number reach n-1. Okay, in other words, you have searched the whole table and couldn't find that key. Okay, but it's very rarely happen anyway, because usually we use a hash table. The assumption is, those load factor alpha. Remember, it's the number of records divided by the size of the table, n divided by n. That number, the load factor, is usually assumed to be less than 1. Okay, if it's too big, if it's very close to 1, something catastrophic may happen. 就是有一些，如果它 那个 load factor 太靠近1，有一些坏事情会发生。什么样坏事，我们马上就会讲到。So in this example, we didn't talk about the probbing, the probbing, the function used in the probbing. But so now we can talk about this. Okay, the first one is the linear probbing. What is linear probbing? Linear probbing is so easy. Okay, basically it's just like give an ordinary hash function. Okay, you just linear probbing is just like you just add the prob number I will be added to the end of the head, like a hash function computation, and then mode m. Okay, it's very, very simple. So if I use this example, the linear probbing is like this. Okay. Okay, the first time it mapped to here, so there's a collision. The second time it's going to be mapped to the next, okay, the following index, because it's going to be this, hk plus 1, right? hk plus 1, so it's going to be this. I mean, if there's a collision here again, it's going to prob hk plus 2, which is here. Okay, so it's very, very simple. Just look for the next, okay? But there's an advantage of doing that, because obviously, if, what should I say, if your key has a collision, then it's going to be inserted at the close place, right? At a place that is very close to where it's supposed to be mapped to, right? So the proximity, okay, can be considered as an advantage of linear probbing, okay? But there's an issue here, okay? What is the issue? Okay, this method you generally produce excellent results, yes. But, sorry, not this one. This one, okay. It's simple, suffers from what we call primary clustering. Primary clustering. What is primary clustering? Primary clustering is like this. Remember, okay, if there's a collision here, as I said, we are going to put this number, this key here, right? This record here. So if there's if happen to be mapped to here again, it will be, this is taken, this is taken, this is taken, so it will be here, right? Okay, so you can see that the records will become like a cluster. The records will be like consecutively, happen consecutively in the table. Remember, we want the record. Usually, we want the record to be distributed evenly in the table. Okay, but what's the problem when there's a cluster? Okay, because cluster, for example, when it maps here, I mean, it will be put here. If we map here again, it will be put here. So you can see, I mean, in the future, if a new record is mapped like anywhere here, this cluster is going to grow very fast, right? Because it doesn't necessarily need to be mapped here to have to increase the size of cluster. The next one, if it's mapped here, it's going to increase the cluster size as well, right? So So cluster like a size may increase like very quickly. Okay, this is like a, so in the future when you do a search, okay, because you are going to, look for your key like sequentially in the cluster, right? When you have a large cluster, it reduces the search efficiency. Okay, so that's like we call this issue as a primary clustering. Okay, where long runs of occupied slots build up. Okay, so it will increase the average search time. The issue is it's going to increase the average search time. So moreover, the long runs of occupied slots tend to get longer, tend to get larger and larger very quickly. So we have an issue for this like a linear probing. Okay, but still, this could be considered like a good approach. Okay, this could be considered as a good approach because it's a simple resolution, simple, and it doesn't require additional space like a linked list. So another idea is how we call double hashing. In the double hashing, okay, I mean, just judging from the name, obviously you have two hash functions, right? So the first hash function, h1k, the second hash function is h2k. So this double hash function basically is like h1k plus h2k multiplied by I, where this I indicate is a probing, the number of number of probings. Okay, so of course this summation may be larger than m, so we need to also mode m, okay, to make sure like this the result is going to be in valid index. Okay, it's going to be a valid index. So this method generally produces excellent results. Okay, but h2k must be relatively prime to m. Okay, why this has to be relatively prime to m? Because like you want, remember, we want this one. Okay, eventually this one. Okay, for different I value, this thing will be mapped to different location in the table, right? So, if you want if this one, h2k and m are relatively prime, then it's going to, I don't know if it's, for example, h2k, okay, it's going to be different. If h2k and m are relatively prime, okay, their GCD is 1, okay, then these two values will be different. Okay, this one, okay, will be mode m. You know this, right? From your discrete math. Okay? Can you prove that? 如果这个，我就把它写成一个这个 P 好了 ，P 跟 N 是 relative prime，then IP 跟 JP 只要 I 跟 J 不一样，它们的那个 mod N 的结果会不一样。这个在离散数学有教过，我非常确定哦，因为我教离散数学，我以前教离散数学，我跳到这边教演算法是不得已的。我原来是教离散数学，我离散数学教了7、8年。OK， 原来蔡老师我跟蔡孟峰老师一起教离散数学。OK， 那所以这个在离散数学有教哦。所以忘记了，回去看一下离散数学，好不好？所以 because of that, okay, so we need to I mean, in order to guarantee this I times H2K is going to, allow us to, to explore the whole hash table. Okay, when I value is different, then we need to make sure H2K and M are, relatively prime. Okay, so in order to do that, okay, one way is to make M a power of 2. Okay, and design H2K to produce only odd numbers, because a power of 2 and an odd number, is automatically, okay, this pair is automatically relatively prime. Okay? So this is like a probing strategy. Okay? So then, okay, we need to analyze this. Okay? We make the assumption of uniform hashing, okay, when we analyze this open address. So each key is equally likely to have any one of M permutations, okay, as it's a probing sequence, okay. So we assume that, okay, and then we have this theorem, okay, for the analysis. Given open address hash table with load factor alpha, okay, which is defined just like what I told you, okay? As long as alpha is smaller than 1, meaning the table is not full, okay? The expected number of props in an unsuccessful search is at most 1 over 1 minus alpha. Why is that? Okay, let me finish this one and then we take a break. Okay, the proof is relatively easy. Okay, so basically, okay, you have to at least do one computation, right? You have to compute the hash function once. So, one prob is always necessary. And with probability, alpha, okay, the first prob hits an occupied slot, and the second prob is necessary, right? So, and, once, because you are, you use one location, so the second prob will go to some other place. So this is assumed like, so if you are lucky, you find like that place. If you are not, so you need to spend, you need to do one more computation. So you need to add 1. But if you are unlucky, the second prob also hit the, occupied location. Then it's going to be n minus 1 divided by n minus 1. The second prob is also going to hit the occupied slot. And then you need to try the third prop, and so on. So you keep doing that. So if you write it into a formula, it's going to be like this. So the first one, and then this is the price you have to pay, and then assuming it's unsuccessful, you hit like a occupied slot. So this is the probability of that, and then you pay the price for the second prop, and then the second prop. I mean, unfortunately, the second prop is also occupied. That's probability is n-1 divided by n-1. Okay, and you keep doing that, blah 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 blah. Okay, so because each of these, n minus, we know n minus k is going to be smaller than n, right? I mean, assuming n is smaller than n, okay? When loading factor is smaller than 1, okay? When loading factor is smaller than 1, then we have, sorry, the other way around. This should be like that. For example, like 2/3, right? 2/3. Okay, if you subtract 1, it becomes like a 1, 2, right? So 0.5 is smaller than like 0.67, right? You get an idea, okay? So basically like you have that. So you can replace each of these, okay, by alpha. Okay, so obviously like this inequality holds. Okay, and then if you expand it, it's going to be 1 plus alpha squared plus alpha cubed plus blah 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 blah. So this is going to be a geometric series. So well, it's I think you know how to compute this. So it's going to be 1 over 1 minus alpha. I mean, ideally, this is like it will terminate like when we reach this term. So actually, not only each of these is like smaller than the n divided by n. Okay, we replace them in this or this by alpha, but also we increase some more additional terms to make it infinite series. Okay. But those additional terms will only increase the size, right? Will only increase the size. So that, again, I mean, this inequality helps us to add like infinite terms here. But once we have that, I mean, we are able to complete this computation. So this is like the number of unsuccessful props, okay? So, I mean, this is really like a little bit informal, okay? But if you want a more rigorous proof, okay, the textbook has that, but I would skip that, okay? And then, okay, from here, okay, because alpha is constant, then accessing an open addressing hash table take constant time. Okay, but even though it's a constant time, okay, obviously this loading factor is the important consideration. For example, if a table is half full, that means the loading factor alpha is 0.5, right? So the average, the expected number of props, unsuccessful one is usually more expensive, okay, than successful one, okay. The unsuccessful one is like 1 over 1 minus 0.5 is 2, okay. So this is not too bad, right? But when the table is almost full, say like it's 90% full, then the expected number of props, okay, again, unsuccessful props, is going to be 1 divided by 1 minus 0.9. It's going to be 10. So you can see that this number increases very quickly, okay, especially when table is almost full. So it also tells you that, okay, for hash table, we usually do not want the loading factor to be too high, okay, in practice. Okay, so that's about it for the first set of slides. And let's take 10 minutes break. When we come back, we'll try to talk about the second set of slides for the hash function.